Okay, so the next show is by Jakob. And this is getting us the proof complexity low bounds.
Thank you. So so we're not going to apply invariance here, but there's going to be variance. So we're going to switch to another topic. So proof complexity lower bounds from graph expansion, and since it's getting late in the day, we'll try to relax a bit and play combinatorial games. And this is joint work with Mladen Miksha and Massimo Lauria. So proof complexity in one sentence, we want to certify the unsatisfiability of CNF formulas, or rather we want to prove that it's hard to certify this. And a general theme, if you look at many lower bounds, are that somehow you look at the CNF formula that you want to prove a lower bound for, you say that it's expanding in some way, and then you argue from expansion that it means that it will be hard to refute this formula. And we know how to do this for resolution and for polynomial calculus, and I'll tell you in a moment what these proof systems are. Polynomial calculus are kind of the excuse for giving this talk in this workshop. But somewhat annoyingly, what expanding means tends to be like formula-specific, some kind of hack. It's very similar, somehow in spirit for different formulas, but still different. So what we wanted to do, we wanted to take a step back and try to abstract away what's going on, and somehow try to do proof complexity lower bounds actually without knowing any proof complexity. So that's the plan today. When you're leaving this talk, you'll know how to prove lower bounds for resolution and polynomial calculus. You'll be totally on top of everything, and you don't even need to know proof complexity. Okay. So that's the plan. So what are we going to do? Well, sort of what most of these proofs do, actually, you look at the CNF formula. So suppose we have this CNF formula here. So we'll somehow look at it, and we'll analyze the structure, and then we'll build a bipartite graph from it. So somehow, these clauses will go together in a vertex, and these will go together in a vertex, and here we have another vertex. And then we look at the variables, and we somehow divide them up also. It doesn't have to be a partition, though. As you see here, y appears several times, w appears several times, but for some reason we're dividing them up into this way. And once we've done this division, it's clear what the graph will be, because we'll have an edge if some variable over here appears in some clause over here. So for instance, w appears here, so we have an edge. X appears here, so we have an edge. W appears there also. So the graph doesn't, it's kind of a boring graph here, but this doesn't always happen, okay? Yeah, good. So, and now we want to prove a lower bound if two things hold. So we want to argue that the graph has to be a very good expander, so that's looking promising so far, and if we also can win a certain combinatorial game on every edge of this graph. So the game is going to be as follows. So we need to be able to win the game. Yes?
So are you saying that if there exists right-hand vertices such that this is an expander and you can win the game?
Good point, thanks. So we're going to look at the graph, and we're going to look at the CNF formula. We are free to build the vertices as we like. Okay. We're free to partition the variables as we like. Once we've decided on these vertices, the graph sort of gives itself, and now we want to argue we need expansion, and we need to be able to win the game. Okay? So the game is going to be, suppose we're going to play on this edge. Then
what's this order of quantifiers? If you can do this,
then it's hard.
If I can do these two things, like if the graph is an expander, if I can win the game, then I get a lower bound. I'll make all of this precise later. So, but just to give you sort of a sense of what's going to happen, so the adversary is going to assign all variables. Suppose we're playing on this edge. So the adversary is going to assign all variables. Then we're allowed to flip these variables if we like. And then when the dust settles, all of these clauses should be satisfied. If so, we won the game. Okay? And we should be able to win this game on every edge.
So wait. The adversary assigns, then we pick the edge, or no? The game is after the edge is chosen.
We're going to play this on every edge. Okay. So you could think of the adversary choosing the edge.
But the assignment is chosen before the edge?
No. The edge is fixed first. The edge is fixed first, yeah, so you should be able to play this on every edge. And again, the adversary assigns all other variables. We assign the variables on the right for this particular vertex, and then we win if all the clauses on the left-hand side are true. Except I didn't specify the protocol fully, like who goes first. Is it we or the adversary? And the sort of conceptual message of this talk is, well, it depends on which proof system you're interested in. If you're happy with resolution lower bounds, then the adversary goes first and then we can respond. However, if you want polynomial calculus lower bounds, it's a stronger proof system, then you need to play a more challenging game. Then we go first and the adversary responds. Okay, it's still the case that we get to decide these variables, but we have to announce to the adversary first how we're going to set them, and then the adversary will adapt. So it's clearly a harder game to play.
And every clause has to be satisfied on the right?
Yes. In this particular, no, only in here. Okay, I don't care about, if we're playing on this edge, only these, right? You can't have a fully satisfying assignment because this will be like an unsatisfiable CNF formula. So that would be a hard game to win. Yeah. Yes?
What advice is for putting all the variables in every vertex on the right-hand side?
Let me get to it in like a few minutes from now. This is sort of just to prepare you for what will come. So this is actually just building on two very influential papers by Ben-Sasson and Widerson and Alekhnovich and Razborov, and it sort of provides a unified way of presenting most proof complexity lower bounds for resolution in polynomial calculus. And thanks to this nice, simple framework, you can also get a bunch of new ones that I hope to get to towards the end of the talk. So what the plan is now, I'll start with a kind of a survey-ish part where I tell you what resolution is, what polynomial calculus is, okay? And then I'll answer all your questions about what this game actually is, and tell you how to prove lower bounds, and then some results that follow from this and some open problems. That's the plan. Okay, so we're going to talk about, it's getting late in the day, CNF formulas, conjunctions of clauses. Every clause is a disjunction of literals. Bar denotes negation. And often, when I talk about k-CNF formulas, the assumption is that k is some small fixed constant. Okay. Resolution. So you start with the clauses of the CNF formula. You can apply the resolution rule to derive new clauses until you reach contradiction. And again, since it is late in the day, let's do a small example to make sure we're all on the same page. Here is a CNF formula consisting of 5 clauses. I claim that it's unsatisfiable. I can represent this refutation in 2 ways, as an annotated list. Here's the list where I'm explaining, so the input, I will call them axioms, and then I explain, if I take clauses 2 and 4 and resolve them over Z using the resolution rule, then I derive X or not Y. Okay? And then I take this new clause and resolve it with the first clause over Y, and I derive X. So this means, so far, I've proven to you that any satisfying assignment to this formula has to set X to true, right? But now let me combine clauses 3 and 5, resolve over Z, and I've derived now not X, so this is clearly a contradiction, and the final formal step is to just resolve these 2 clauses to derive the empty clause contradiction. Okay, and I can also represent this proof if I like as a DAG, where I show how the derivations were made. And in this particular case, it happens that it's a tree, and then I say it's a tree-like resolution proof. Okay. So the most important proof complexity measure that we care about for resolution and for any other proof system is size, which for resolution we can just count the number of clauses. It's never worse than exponential in the number of variables, and there are matching lower bounds. In fact, not only in the number of variables, but slightly stronger even in formula size. Another measure that we're going to care about is width, which is the size of a largest clause in the refutation. And it will be clear in a little bit why this is a helpful measure to look at. And just to see here that the length of this is 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is the widest clause, so the width is 3. Okay? So, but let's move on to a more fun proof system, that is polynomial calculus. So now we interpret clauses as multilinear polynomials over some field, your favorite field. So x or y or not z gets translated to x bar times y bar times z. You're sort of looking at, if this clause is supposed to be false, then not x, not y, and z all have to be true. That's how we should think about it. Okay?
So not x is a new variable now?
Yes. So this is formally, there are bar variables and there are non-bar variables. They're formally distinct. Okay? And we have a particular axiom that tells us what the meaning of negation is. So these are x and x bar are formally distinct variables, but they're related by this polynomial. That is an axiom. And I also have x squared minus x. Or alternatively, I could just work in the ring where I mod out by all of these guys, and I only work with multilinear polynomials. And then I can take linear combinations. I can multiply by a variable. And my goal is to derive 1, which is possible if and only if the formula is unsatisfiable. Okay, and this is just formalizing what Gröbner basis computation means. Okay. And now if I set it up in this way, complexity measures, size and degree. So every clause turns into a monomial. So in a resolution where we're counting clauses, now we'll count monomials, and we'll write the polynomials. We'll insist on a very specific, stupid polynomial representation, namely as linear combinations of monomials. So the size is going to be the total number of monomials that you see in a proof, and degree is the largest degree of any monomial. And you see that clause width will turn into monomial degree. Okay? So size and degree. And it's not so hard to see that polynomial calculus is at least as strong as resolution, because you can simulate the resolution refutation line by line. So if you look at the first resolution step we did, we resolved these two clauses, x or not y or z, and not y or not z, and derived x or not y. This is how I will do it in polynomial calculus. First, I just take these two clauses, and I sort of weaken them to speak about the same variables. So I multiply by z here. And then I just use the fact that I have this semantics for the z variable, and I multiply it by all the other variables, and then I just add up, and boom, here's the clause I wanted to derive. Okay, and maybe you don't see this totally online, but offline with pen and paper in just a minute, you'll figure that this always works. Okay. Good. So let me tell you some of what we know, some classic results for these proof systems. Random KCNF formulas is my first example. So if you just sample delta n k clauses over n variables, so for 3 CNFs, delta 4.5 is enough, then asymptotically, almost surely, you'd get an unsatisfiable CNF formula. And this is exponentially hard, both for polynomial calculus and resolution. A slightly more interesting example are pigeonhole principal formulas, very heavily studied in proof complexity. So encoding that n plus 1 pigeons don't fit into n holes, except we want an unsatisfiable CNF formula. So of course our CNF will say that this is completely possible. Every pigeon is getting a hole. For every hole j, it is the case that no two pigeons I and I prime go into that hole. Then I can vary things a bit. I can also say, oh, this is actually a mapping. Every pigeon gets exactly one hole. And then if I have a heightened sense of fairness, I say, well, then every hole should also get a pigeon. I have a perfect matching. Resolution doesn't really care. I mean, all of these versions of the pigeonhole principle are like dead hard for resolution. For polynomial calculus, it's more interesting. So the vanilla version consisting of this two type of clauses is exponentially hard. If you actually say that you have an onto functional pigeonhole principle, so perfect matching, then it's actually easy. It's not so hard to see over any field. And for the versions in between, if you just have functionality axioms or just onto axioms, actually it hasn't been known. Okay? And the third, and this in particular, this shows also that because of the onto functional pigeonhole principle, this shows that polynomial calculus is strictly more powerful than resolution. Another interesting class of formulas are encoding the handshaking lemma, or that the sums of degrees of vertices in an undirected graph is an even number. Okay, so we encode this in a sneaky way by labeling vertices 0, 1 in such a way that their sum is an odd number. Edges will be the variables, and every vertex now has a constraint saying that the parity of the truth values of my edges incident to me is equal to my label. So this vertex wants x and y to have odd parity. These are these two clauses. And this vertex wants y and z to have even parity, and that's these two clauses. Okay? And if you plug in an expander graph, this is exponentially hard for resolution. For polynomial calculus, if we're not over a field of characteristic 2, but if you are over G of 2, then just do Gaussian elimination, and it's easy. Okay? So the field can matter a lot. Okay, so that's like some of the classic results. Okay, so how do you prove lower bounds? Well, it turns out that width and degree are very helpful measures to look at. So one easy thing is to say, well, if I have an upper bound on width or degree, say W, then it gives an upper bound of size that is essentially n to the W, and this is tight in the worst case. What is not so obvious is that if I have a strong enough width or degree lower bound, then that gives me a size lower bound. So here's the formal statement by so this is by Russell in Pagliazzo, Pavel Putlak in J.G. Skal for polynomial calculus, and then for from Benzozon and Widerson for resolution. So if I can prove, if I have a width or degree lower bound W, then the size is exponential in W squared divided by the number of variables. Okay, so what this means is that if I can prove a lower bound that is growing asymptotically faster than square root n log n, then I have a super polynomial lower bound. If I can get a linear degree or size lower bound, then I have a truly exponential size lower bound. And this is also tight. We know that there are no implications for if you actually just reach square root n, then you can still be very easy with respect to size. And now, this is like a key theorem. You can use it to prove most resolution lower bounds in the literature. There's a well-developed machinery to prove with lower bounds. And we also have lots of other tools for resolution. For polynomial calculus, there are two problems. Firstly, it's way harder to prove degree lower bounds. We're not very good at it. And secondly, this is sort of the only game in town. We don't have other good tools. So this is, there are lots of nice open problems there. And so, okay, so now I'm going to tell you soon about how to prove the lower bounds, except if you were paying attention, there's a problem if you want to use this to prove pigeonhole principle lower bounds, because the proof width is obviously very large here because, you know, the initial clauses are very large. So what do? For the pigeonhole principle, we hit the formula with a random restriction, so we just restrict pigeons so that they can only go to, say, a constant number of neighbors, randomly chosen. Okay, and then you get a graph pigeonhole principle, and you have them in all flavors, vanilla, onto, functional, etc. And now if I can prove a strong width lower bound for these formulas, then that gives me strong size lower bounds for these formulas, which must obviously hold also for the unrestricted formulas. Plus, we sort of obsess in proof complexity about the pigeonhole principle formula, so we're also very interested in graph pigeonhole principle formulas. Yes?
So you said that you already have exponential lower bound for pigeonhole principle. So you are trying to give a different proof, or what's?
So for polynomial calculus, we don't know it if you throw in functionality axioms or onto axioms. For instance, we only have it for the vanilla version, where only pigeons get holes and holes get pigeons. But as soon as I say that every pigeons get exactly one hole, then the lower bound breaks.
So how was width defined? So, I mean, I forget, so there are large axioms versus large derived clauses. Are you differentiating between
No, the width is just the largest clause that you have in the proof. So if there are large initial clauses, you have to deal with them some way because they're going to mess things up for you.
Then the lower bound doesn't hold, presumably.
Well, it holds, but it's sort of right. Yeah. This, as I stated it, it's only for KCNFs. Yes, thanks. Yeah. So I was sort of assuming in the statement that.
It's a constant width input.
Yeah, well, there was a K there. I forgot to say that. And that's sort of, I said at the beginning that this was supposed to be a constant. I could have said it again more clearly. Yeah. There is a general, what will happen is the initial degree will be subtracted from this. Right. Okay, so then so the statement is still true, but you have to subtract the degree there, and then it will be no fun. You won't get anything. Okay. So how do you prove lower bounds? Well, via with. Okay, good. How do you prove with lower bounds? From expansion. So here's a simple example. You just take the CNF formula and you look at the clause variable incidence graph. Every clause gets a vertex, every variable gets a vertex, every edge is just that a variable occurs. Okay, and now we're going to look at expansion. In particular, we're going to look at boundary expansion or unique neighbor expansion. So that means that you look at a set of clauses, you look at their neighbors, and you look at the neighbors that are unique neighbors, that are in the boundary. So these three guys. We're only interested in them. Okay? Which means that actually if you look at complete graphs will be bad for us because the unique expansion is like non-existent. The problem now, and this works great, but the problem is that if you start thinking about pigeonhole principal formulas or Tseitin formulas, for instance, suppose you have like a Tseitin formula which encodes parity constraints. Well, you know, there are going to be many clauses to encode each parity constraint, and this is not going to be an expander at all. Okay? So we want to build another graph that somehow captures the combinatorial structure. So this is what we're going to do. So we're going to do this basically. Guided by our understanding of the formula, we partition the variables into clauses. And then actually we're going to add something down here at the bottom, a special clause set that I'll call E, that will not take part in the graph. And then I'll somehow divide the variables, and I'll keep track of the overlap, how many times the variable appears over here. And I want that to be some constant. Here the overlap is 2. I want it to be bounded. And then I build the bipartite graph that I just told you before. And the role of this E set is basically just, it's going to decide which kind of truth value assignments we're interested in. And for those of you who know, for pigeonhole principles, you should think about the E set making sure that we only consider partial matchings, for instance. And then, so we're going to play this combinatorial game. So here it is, exactly specified. So the adversary chooses a total assignment. So the edge is pre-specified. So the edge is fixed first. We know which edge we're playing on. Okay, the adversary chooses a total assignment, but it has to satisfy the filter set. It has to be like a valid assignment. Okay? We get to modify it on the variables in the right hand side vertex. Okay? And then we win if our assignment is also valid, it satisfies the filter, and it satisfies the clauses we were playing on. Okay? So now let's play this game. So this is hopefully exactly the same instance. Okay. So let's play on this edge. So can we win? No, we can't win. Because suppose the adversary plays x is true and all other variables are false, then this clause is false, and we can't do anything about this because we can't even flip those variables. So this is, you should not build your graph in this way. This is a bad graph. Okay, so a more interesting example, let's play on this edge. Can we win? Again, the answer is no. The adversary again plays w, y, and z false, and x we don't really care, and let us see why. So I have to satisfy the filter, and I can only flip y, which means that I can't flip y, because then I'm screwing up the filter. Okay? And I can't flip z because it's not in v2. But if you now look at f1, it means that I would have to satisfy both x and not x, and I can't flip x to do that. So we're losing on this edge. Okay, so what about this edge? So here things are better, because the adversary goes first, and then whatever the adversary does, we just set x to be the OR of y and z. So we're not touching y or z, so clearly we're not violating the filter. And if you look at what f2 said, it's just the encoding that x is the OR of y and z. Okay. So if you want to do resolution lower bounds, you want that all edges should be of this type. Okay, is this sort of clear? Okay, so again, the boundary of a set is just the unique neighbors on the right. And now let's say that a resolution expander is a graph that has good boundary expansion, and I can win this game on every edge. Okay? Then the claim is that if I have a CNF formula, and if from it I can build an expander graph such that all sets of size at most s expand by a factor delta, and I can win the resolution game with the filter set E, and the overlap is at most L, which you should think of as a constant, then...
So overlap is the number of times a variable appears?
Yeah. So the overlap here was 2 again. So think of it as a constant. Then the interesting thing, like the interesting term here is delta S, which will be, this will be a positive constant, this will be linear, so now I get like a linear with lower bound. Okay, and this is essentially Bensason and Wigderson.
But Bensason Wigderson didn't even have the game. Oh yeah.
They sort of have the game. Okay, but they don't express it this way. So let me actually just, to give you 1 or 1.5 technical slide, let me sketch to you sort of how the proof would go, and you'll be able to fill in the details offline. So suppose that we have a resolution derivation starting from this formula, and every clause has width at most this, okay? Then I'll define some kind of subsets of clauses in my formula. I'll call it the support, and I'll prove 2 things. That the support is fairly small, and that the support of a clause together with this filter set actually implies the clause. Okay, I'm going to prove that on the next slide. If I can do this, then since the support is so small, then actually the support union, the filter set, is a satisfiable set. Okay, but if it is satisfiable and implies C, then that means that C is also satisfiable. So it's not contradiction, so we didn't derive contradiction in this small width, QED. Okay. So what's the support going to be? Well, the support is going to be, I'm going to somehow throw in a new clause down here. And I'm going to look at if this would have been a vertex, you know, what neighbors would it have had? Maybe these 2. Okay. And then the support is going to be all of the vertices in here, sort of, such that the unique neighbors of this set land inside the neighborhood of this clause. So I'm going to find the support of a clause as the largest set that is of size at most s, and such that the unique neighbors are all contained in the vertices of variables that the clause also mentions. And now I just have to prove 3 things: that this is well defined, because that is not at all clear, but it is, by expansion. Then I have to prove that the support is small. That's also true by expansion. And then I have to prove this implication, and this is where the edge game comes into the picture. Okay, and this is sort of going fast, and it's getting late, but really, this is all there is to it. If you just take these definitions, you would be able to figure this out. And so I won't have time. We'll do something very similar. So jumping ahead a bit, we'll do something very similar for polynomial calculus. The definitions will be the same. The proof will sort of somehow be the same, except that it gets way more messy, and I don't have time to say anything about it. We'll get to polynomial calculus. Okay. So, but once I have this, so now, you know, if you're going to, in your computational complexity course, you're going to give just 1 lecture on proof complexity. Now you can do all the proof complexity lower bounds. For Tseitin, the left-hand vertices are going to be the parity constraints. So all clauses encoding 1 parity constraint goes into 1 bag. The variable vertices are going to be singletons. There is no filter. We're interested in all assignments. And you just look at the graph, and if the underlying graph is an expander, is an edge expander, then your graph that you're building will be an expander with the same parameters, and the lower bound follows. Okay? And for the pigeonhole principal formulas, the left-hand side are just going to be the pigeon axioms, like every axiom saying that a pigeon gets a hole is its own vertex. The variable bags are going to be talking about holes. So every variable mentioning hole j goes into the j bag. And then we'll have all whole functional and onto axioms. They go into the filter so that we want to actually only consider maximal matchings. And then again, if you look at the graph version, you basically, this just gives you back exactly the same graph as you had. So if the original graph was an expander, then this graph is an expander and you have a lower bound.
In both cases, the games are easy to win.
Yeah, the games are like, yeah, because in the Tseitin formula, we're going to play, okay, good. In the Tseitin formula, the adversary says, I want you to satisfy this parity, okay? And you said, fine, how do you set all other variables? And then you decide whether you want to flip a variable in the parity or not, okay? And for the pigeonhole principle, you say, okay, good, give me a partial matching. And if the pigeon we're playing on is not satisfied, then I just make sure that no other pigeon goes into that hole, but my pigeon goes into that hole. Note that that can make other pigeons very unhappy, but I don't care about other pigeons. I just care about the pigeon we're playing on. Does that make sense? Okay, so this gives us resolution with lower bounds, but it couldn't give us polynomial calculus lower bounds because both Tseitin and Onto functional pigeonhole principle are easy for polynomial calculus. So something has to change, and what's going to change is we're going to switch the order of the players. So we're still going to play on an edge, FV, but we have to go first and say how we want to set the variables in V, and then the adversary sets the other variables. And now it becomes very hard to win on Tseitin, right? Because we have a parity of several variables, and I set the first, and then the adversary says, okay, I see, and sets the rest so that the parity is false. So now we can't win. What we need to do is when we're playing on a variable bag, we somehow need to make sure that we set all clauses in F to true, and we also have to, if we're touching a clause in the filter set, then we have to satisfy it. It's okay to just miss clauses in the filtering set, but if we're touching it, we have to satisfy it. Okay? So here is our example graph again. So remember that we lost in the resolution game is an easier game. So if we're losing already there, then we're screwed. So we lost on this edge, we lost on this edge, we won on this edge in the resolution game. So now let's see what happens if we want to play the PC edge game, the polynomial calculus edge game. So now we actually lose because if you think about it, so we're going to touch the filter set. So we have to set y to false. Okay? And then we have to set x, but x was encoding that y or z was true, but we don't have control over z. So of course, basically this is saying that x and z have to have the same value, but we don't have control over z, so the adversary will just play the opposite value. And we go first, so now we lose. Okay, but suppose we play on this edge, well then we can win, and this is sort of a small trivial example, but let's see why. We set x to true and y to false, so now we satisfy, because x is true and y is false, that satisfies all the clauses in F3, and we're also satisfying the filter. Yes?
So this characterization doesn't depend on the field at all. So you can't distinguish, I guess.
Very good point. This will only work for lower bounds that are true over any field. Yes. Yes. You're like 9 slides ahead of me, but you're absolutely right. Yeah. Okay, so now we just have the same, instead of a resolution expander, let's talk about the polynomial calculus expander. If it is a boundary expander, and if on every edge we can win the edge game. Okay. And then we get exactly the same statement that the degree is now delta S, so the expansion factor times the size we can guarantee for the expansion divided by the overlap, which will keep to something constant. And this, I want, again, sort of the definitions I gave for resolution are actually very similar to what we'll do here, but the technical details, we'll have to look at different polynomial ideals and reduce modulo them, and then grow and shrink these ideals and have control over what happens. And expansion is going to be very important. Okay, so do we have time for, okay, so what happens? So this is a way of basically giving all lower bounds for polynomial calculus, except the ones that depend on the characteristic. And we can do some new lower bounds that I hope to be able to tell you about, the functional pigeonhole principle and also for graph coloring. Okay, the pigeonhole principle, what's known? So I said for resolution, Haken proved that the vanilla version is hard, but his proof actually extends to all versions. For polynomial calculus, Aleknovich-Razborov proved that the vanilla version is hard. Ries observed that the onto functional pigeonhole principle is easy, and in between, it hasn't been clear. Okay, but so what we did is we observed firstly that actually Aleknovich-Razborov did take care of the onto version also, but they just didn't say it or observe it. And for the functional pigeonhole principle, it turns out it is hard. And how we're going to prove it is we're just going to build a graph, and it's essentially going to be the same graph as before, except on the right, we're going to have not holes, but we're going to, like in VJ, oh, whoops, that was not intentional. We're going to have all variables speaking about, like we fix a hole J, we look at all pigeons that can go into that hole, and all other holes they could go to. And all of those variables will somehow be related to the right-hand vertex J. And now, once we have this, and once we have this PC expander game, it's just something that you easily verify with pen and paper. Now we're good. Now we have a lower bound.
So these bounds are typically proved by taking the complete pigeonhole graph and then taking a random subgraph of it, is it?
Yeah, but this is like something slightly stronger. I mean, you can just, as long as you do it adversarially, as long as you guarantee me that you have a certain expansion, then we get a lower bound. But in particular, if you want it only for the complete graph, then you'll take a random restriction, and that will give you an expander. Yeah, or there is a way to restrict it to get an expander. Another formula that is interesting is graph coloring, stating that a graph is k-colorable. So for resolution, we've actually had average case lower bounds for Erdős-Renyi graphs with the right edge density. This is by Paul Beam and others. For polynomial calculus, nothing has been known, very annoyingly. No lower bound whatsoever. And in particular, it turns out that there is a line of work that proves that there are algorithms based on not polynomial calculus, but on Nullstellensatz that works really well in practice and solves coloring for graphs with thousands of vertices. And they write in this paper, this is like an award-winning sequence of papers in the OR community, and they write, we cannot find hard instances for this. I mean, they know what NP is. They know that they probably didn't solve an NP-complete problem, but they're explicitly asking for, like, show us a hard instance. Okay. So here's a hard instance. What we're going to do is we're going to use the fact that we now know that functional pigeonhole principle is hard. Okay? And we're going to reduce functional pigeonhole principle instances to coloring, and we're going to show that somehow polynomial calculus is strong enough to compute this reduction. And we're running out of time, I guess.
4 or 5 minutes.
Okay, that's plenty. So I'll just sort of give you some high-level pictures how this goes. And I should say that we use like a 0-1 encoding for these variables. So these variables will just be set to 0-1. And you have axioms saying that so xvi is just which color I the variable v gets. And then you make sure that every vertex gets just a single color. The papers over in the OR community use a slightly different kth root of unit encoding, but you can take our proof and make it work for their encoding also. So, good. So we have a functional pigeonhole principle instance on an expander graph with left degree k, where k is like the number of colors. And so for every pigeon I, we have k available holes. And we're going to think about every pigeon as being a vertex, and we color it by the edge it chooses. Okay? And now if pigeon I cannot take edge C, and pigeon I prime cannot take edge C prime simultaneously because they would end up in the same hole, then we think of this as, okay, you can't color I by C and I prime by C prime simultaneously. Okay, so this is kind of coloring, but it's not coloring. But it's coloring-ish. And what we'll do is just we'll build a gadget to make it into coloring. So here's the gadget. for 4 coloring. So these are going to be pre-colored vertices that we'll take care of later. And this is just saying that if pigeon I and I prime both take the green edge, then they collide. Okay? So any coloring for these pigeons are going to be okay, except the green-green coloring. And to see why, is suppose that pigeon I takes the green color, then we have to use up all other colors for the clique, and so the rightmost vertex in the gadget has to be green. And now you have exactly the same situation on the right, where the leftmost vertex in the gadget has to be green. But any other coloring will be okay. And if you wanted the colors to be different, then you just identify the 2 vertices instead. Good. So that's coloring lower bound, but worst case only. But it's at least an exponential lower bound for graph coloring. Okay, so Grosvenor bases provably don't solve NP-complete problems. Great. Some open problems. Prove lower bounds for instance, independent set for graph coloring. In average case, there's what seems to be a slightly easier problem, so-called dense linear ordering formulas that we don't know how to prove degree lower bounds for. I'd be very happy to talk to you about it. For resolution, we have many other tools. For polynomial calculus, this is not the case. So for instance, it's still consistent with state of the art, and maybe Grosvenor basis actually solves the K-clique problem efficiently. We also don't know what happens when you blow up the number of pigeons to be n squared or above, because then the degree lower bound doesn't give us anything. That's another great problem. And as Russell noted, so our technique only works independently of the field. Aleknovich-Razborov has actually another version of the technique that can deal with different characteristics. It would be great if we could somehow merge these 2, because that would allow us to prove some lower bounds that we don't know how to do today. So, we're at the end of the day. Thanks for sticking around so long. So what I tried to present to you was a unified framework for most proof complexity lower bounds for resolution and polynomial calculus. And I think what's nice, it's exactly the same framework. The only difference is who goes first in this game, which I think is nice. And then this gives us lower bounds for functional pigeonhole principle and for graph coloring. We'd like to extend these techniques to work for other tricky formulas and to find other tools than degree lower bounds for polynomial calculus. Thanks.
Questions?
Really at the end of the day.